Hi, welcome back to CS560, and this is the lecture 3. And the topic of this lecture is the growth of functions. And in this video, I will cover the first part of this lecture. So I will introduce the notations of asymptotic notations. Includes the big O notation, big omega, and theta notations. So I believe we are already used the theta notation to describe the running time of insertion sorts and merge sort in our last lecture. And today we're gonna first give the formal mathematical definition of these notations. And on Thursday's lecture, when I come back to the classroom, I will give more concrete examples using the notations. So first, let's have a review of the running time of the two sorting algorithms that we analyzed in our last lecture, in our last class. So we have insertion sorts and merge sorts. And for the worst case running time of insertion sort, we use the notation T of n to represent, to denote the running time. Okay, so for the worst case, the running time for insertion sorts is written as the theta of n squared. And for the average case for merge sorts, the running time is written as the theta, big theta of n times log n. And when we first introduced the theta notation in our previous lectures, we use a rough notation that theta means T of n runs as fast as grows as fast as the function n squared. Okay, and for merge sorts, the theta notation means that T of n grows as fast as the function n times log n. Okay, so let's have some concrete numbers and compare the true running time for these two sorting algorithms. So let's make this comparison a bit extreme to let the insertion sort algorithm run on the very fast computers. That means we let the constant before n squared to be 1. Okay. And we let the merge sort algorithm run on the very slow computers, and we give it a very big constant. So that means even when the input sequence is very short, for example, n equals 10, and the running time for the merge sort is still quite big because the constant is big as 100. Okay. So because now we have these concrete numbers, so we can actually plot these two functions. Okay, so in this plot, the green line is the merge sort, it's a function of merge sort, and the red line is for insertion sort. As you can see, if we limit n between 0 and 500, so when n is less than 500, the green line is always above the red line. That means it always takes more time to run a merge sort than insertion sort on the sequence that has fewer than 500 elements. Okay. So we also say that the function 100 times n times log n grows faster than a function of n squared when n is small. So what if we increase n, the number n, a little bit? So now we increase the range of n to from 0 to 1,000. Okay. So when when the number n reaches around the point of 1,000, we can see that the two lines, they merge, they meet each other. That means, okay, around n equals 1,000, the two algorithms are actually running equally fast. They take equally amount of time. Okay, so actually you can do the computation by using, for example, n equals 1,024, which is 2 to the power of 10, to make a simple comparison. So that means as n grows to a threshold point, the running time for insertion sort, which is in red color, actually grows so fast that it almost catch up with the merge sort. So what if we further increase the number n to let it be larger than 1,000? So now we let n from the range of 0 and 2,000. We can see that as long as n is large enough, the running time for insertion sort will eventually be larger than that of the merge sort. Therefore, although for the merge sort we have a larger constant, 100, right? So as long as the n is large enough, then this constant becomes irrelevant, because the function n squared will eventually grow much faster than the function n times large n, log n. Okay, so hopefully by comparing these two plots, you can have a sense of how merge sort is more efficient algorithm than insertion sort if n is large enough. Therefore, here we introduce the concept of asymptotic efficiency. So in general, when we analyze the efficiency of algorithms, it is the order of growth of the function, of the running time function t of n, that really matters. So the concept of asymptotic efficiency means that how the running time increases with the input size n in the limit as n increases without bound. In another word, we should not only consider normal ranges of n or small values for the number n, we should consider the extreme cases where n can actually increases to its limit, can be infinitely big. So we should consider under that extreme conditions how the running time t of n looks like. And we should always choose an algorithm that is asymptotically more efficient. So when the n is big enough, we should always choose the function. We should always choose the algorithm that has a running time function that grows slower. We will first introduce three asymptotic notations, which are the theta notation, big O notation, and big omega notation. And these notations, they apply to functions. For example, on the left, there is a generic form of quadratic function, which is a times n squared times b plus b times n plus c. And we can write that this quadratic function belongs to the theta of n squared. Okay, so this is how we use these asymptotic notations. And these notations, they are used to describe the asymptotic properties of functions. For example, the quadratic function on the left, or it can be a exponential function or logarithm function or whatever functions that you want to estimate its asymptotic properties. And usually these notations are used to characterize the running time of algorithms. Okay, but sometimes we can also use such notations to characterize the efficiency of memory space usage, like how much memory, how much RAM memory that the algorithm costs, just like the analysis of the running time. Let's first look at the theta notation. So for a given function g of n, and the notation theta of g of n is defined as a set, and the elements of this set are functions. It is a set that each of its elements satisfies that there exist positive constants c1, c2, and n0 such that the function fn is greater than or equal to c1 times g of n, and the function f is less than or equal to c2 times g of n for all n that are greater than n0. Okay, so this is a formal definition of the theta notation of g of n in a mathematical language. So it is defined as a set, and the elements of the set is all the elements are functions, and those functions satisfy this statement, satisfy this condition after the column. In other language, a function fn belongs to the set theta of g of n if there exists positive constants c1 and c2 such that it can be sandwiched between c1 times g of n and c2 times g of n for sufficiently large n. So because theta of g of n is a set, so strictly we should write fn belongs to this set, right? But usually for simplification, we usually write fn equals theta of g of n. But it's useful to have it in your mind that the theta notation of a function means a set of functions. And if we write fn equals to theta of g of n, it simply means that this fn is just one member or one element of such a set. We can draw an intuitive picture of the theta notation. So this picture shows that to the right of the value n0, right, the value of function fn, which is indicated by the curve in the middle, it always lies between c1 times g of n and c2 times g of n. Okay, so the case of fn is a member of theta of g of n can be visualized in this way, that fn lies between the two curves. So we can also say that g of n is a asymptotically tight bound for fn, because g of n is both the lower bound and also the upper bound for fn. And it requires that for every member, fn and gn itself must be asymptotically non-negative. They should be above 0. Now we can use the mathematical definition of the theta notation to prove many of the operations that we used before. So for example, we used to say that we can ignore the lower order terms, right? So for a function, fn equals 1 over 2 times n squared minus 3 times n, we can write it as theta of n squared. Okay, so we say that n squared is a tight bound for the function fn, and we simply ignore the lower term 3 times n. And we can use the definition of the theta notation to prove why this is the case. Okay, so here's a brief justification. So according to the definition of theta notation, we need to determine 3 positive constants, C1, C2, and N0, such that the function fn in the middle here should be greater than or equal to C1 times n squared and be less than or equal to C2 times n squared for all n that are greater than n0. Okay. So if we now observe these inequalities and we just divide it by n squared, it'll become this form, right? So 1 over 2 minus 3 over n should be greater than C1 and less than C2. Okay, and because n is an integer, so it ranges from 1 to infinity, right? So if we observe the right inequality, we can see that if we choose any constant C2 that is greater than 1 over 2, the right inequality always holds, because n is always a positive number, right? So that means this thing in the middle is always smaller than 1 over 2. And if n is infinitely big, infinitely large, then the function in the middle will approach 1 over 2, but it should never be greater than 1 over 2. So we can choose C2 equals, choose any C2 that is greater than 1 over 2 to make this right inequality hold. And then for the left inequality, we can see that if n is 1, then the thing in the middle is negative, right? 1 over 2 minus 3 is negative. And for n equals 2 and 3 and 4 and 5, they are all negative. The thing in the middle is always negative. But for n equals 6, then the middle expression is 0, right? So in order to choose a positive constant C1, then we should at least use n equals 7. Okay, so when n is larger than 7, then the middle term becomes 1 over 14, right? And if n is larger than 7, then the middle term is greater than 1 over 14. Therefore, we can choose any constant C1 that is less than 1 over 14, and the left inequality always holds for any n that is greater than 7. Okay, so combining these left inequality conditions and the right inequality conditions, we can show that by choosing C1 equals 1 over 14 and C2 equals 1 over 2 and n0 equals 7, we can always make this inequality holds, right? And that means the inequality above always holds. Therefore, the notation, the function fn belongs to the theta of n squared. This statement is true. Okay, so this is how we formally prove that, how we can ignore the lower order terms. we should notice that in the example we just showed, there are other choices for C1, C2, and N0, as long as C1 is smaller than 1 over 14 and C2 is greater than 1 over 2. So, but the important thing is that some choices exist, right? As long as some choices for C1, C2, and N0 exists to hold the inequality, then we can say that the function fn is bounded by n squared, can be written as theta of n squared. And so the existence of these constants are most important thing that we want to prove. And also, these constants, they actually depend on the coefficients of the function, right? So because currently our function is 1 over 2 times n squared minus 3 times n. So what if those coefficients change? Then the C1, C2, and N0 that can be used to hold inequality also change. Next, we can use the mathematical definition of theta notation to prove that why the higher order terms in the functions cannot be ignored. Or in this particular specific example, we want to show that why this function 6 times n cubed or 6 times n to the power of 3 is not a member of theta of n squared. We cannot use the notation theta of n squared to describe the asymptotic property of 6 times n cubed. So let's suppose that there exist C2 constants, positive constants C2 and N0, such that the function c times n cubed is less than or equal to C2 times n squared. And it holds true for all n that's greater than n0. So what if we divide the inequality by n squared? It'll become n is smaller, is less than or equal to C2 over 6. Okay? But as we see, this is a contradiction because n can be arbitrarily large, right? Because we need to prove that n it should hold for all n that's larger than n0, and that means n should be arbitrarily large, but this is a contradiction here. Therefore, we cannot write 6 times theta, 6 times n cubed is equals theta of n squared. So in an informal language, we should say that the cube function always grows faster than the square function. So the cube function cannot be sandwiched by a quadratic lower bound and a quadratic upper bound. Now we'll see an example of a generic quadratic function. So if the function is in this form, fn equals a times n squared plus b times n plus c, and the coefficient a is larger than 0. So how do we show that this function belongs to theta of n squared? Right? So similar to the previous examples, we need to find positive constants C1, C2, and N0 such that these inequalities hold. Right? The function fn in the middle should be greater than or equal to C1 times n squared and be less than and equal to C2 times n squared for all n that is greater than some threshold n0. Okay? So let's manipulate these inequalities a little bit and move the C1 term and C2 term around. So now we have two inequalities. The first one is that this quadratic function, in which the coefficient is for n squared is a minus c1, this quadratic form should be greater than 0. And the second quadratic form, where the coefficient for n squared is a minus c2, should be less than 0, should be lower than 0. So remember the properties of a quadratic function. If we want a quadratic function to be above 0 for all n that are arbitrarily large, then we must let the coefficients be greater than 0. Right? So that means the curve of the quadratic function should have a opens towards upside. Right? And if we want a quadratic function that are smaller than 0 for arbitrarily large n, then these coefficients a minus c2 should be negative, should be smaller than 0, so that the open is towards downside. So the right function, the right quadratic form should have this form, and the right quadratic function should have the blue form, right? And in order to have these inequalities hold, we need to have a should be between c1 and c2, right? But that's not enough. In order to make the left quadratic form be larger than 0, we should let n be bigger than this point, right? We should let n be bigger than the right root of the quadratic. If the quadratic function equals 0, if we solve the function, we should have the root here, and we should let n be greater than this root, so that because the quadratic function is increasing after the root here, so such an inequality can hold. And similarly, for the right quadratic form, we should compute the right root here, and we should let n be greater than this root point. Okay, because to the right of this root point, the quadratic function is smaller than 0. Therefore, we can make n be greater than the larger root of the two equations. Right? We solve the two equations, and we just make sure that n is larger than the larger root. Therefore, if we find some c1 and c2 to make it easier to solve the two equations, for example, if we let c1 equals a over 4 and c2 equals 7 times a over 4, then it'll be just easier for us to solve the two equations. And we want to make sure that we need to choose n0 to be the relatively larger root of resulting from solving the two equations, right? So after choosing c1, c2, and n0 like this, we can make sure that these two inequalities hold for all n that are greater than 0. Therefore, we eventually show that Fn is theta of n squared. So that's how we prove using the mathematical definition for a generic quadratic function. So now let's look at the theta notation for general polynomial functions. So for example, if we have a polynomial function like this, which is a summation of ai times n to the power of I, in which I ranges from 0 to d, and ai are constants, and for the highest order term ad should be greater than 0. Okay, so if we have such a form of generic polynomial functions, then we have that P of n is theta of n to the power of d. Okay, so that means n to the power of d is a tight upper bound and lower bound for this generic polynomial function. And here we don't give the proof, and all you need to do is to remember this rule. And the rule of thumb is just to choose the highest order, to see what the highest order is within these polynomial functions. And this polynomial function is always bounded by a highest order, which in this case it is n to the power of d. So, and for any constants, because we can always write it as a degree 0 polynomial, right? Any constant can be written as something to the power of 0, and then it can be expressed of theta of n to the power of 0, or simply theta of n. So much for the theta notation. Now let's look at the big O notation. So we know that theta notation asymptotically bounds a function from both above and below. So what if when we only have an asymptotic upper bound? Then in this case, we use the big O notation. Okay, so more formally, the definition of big O notation is also looks quite similar to the definition of theta notation. So for a given function g of n, then the big O of g of n is defined as a set of functions, and the elements in this set satisfy that there exists positive constant c and n0 such that fn is greater than 0 and less than or equal to c times g of n for all n that are greater than n0, right? So you can see the similarity between these statements from the definition of the theta notation. Here we just use one c constant, right? Because we just define a upper bound for fn. Okay, so if we have draw a intuitive picture for the big O notation, then we will have that to the right of the points of n0, the function fn is always below c times g of n. Okay, so we should also note that, see the relationship between big O and the theta notation, because fn, if fn equals theta of g of n, then it naturally implies that fn equals big O of g of n, right? Because theta notation is a stronger notation than the big O notation. So if you have a theta notation, if fn equals theta of g of n, which is shown on the right figure here, right? So if fn is theta of g of n, then fn is bounded by c2 times g of n and c1 times g of n. Then because the theta notation implies that fn is greater than c1 times g of n, then it naturally leads to fn is greater than 0, right? So if g of n is a tight bound for fn, then it is naturally a upper bound for fn, as denoted by the big O notation. Now we have met both theta notation and big O notation. So now let's talk about the tightness of the bound. So In the language of set theory, the theta notation, the theta of g of n is a subset of the big O notation, of the big O of g of n. So as indicated by the previous intuitive picture here, so the theta Fn equals theta of g of n naturally leads to the fact that Fn equals O of big O of g of n. Therefore, theta of g of n is a stronger condition, is a stronger notation than the big O. So, for example, for any quadratic function Fn in this form, then because we already proved that Fn equals theta of n, theta of n squared, then it means that Fn is also big O of n squared. And more surprisingly, any linear function Fn equals a times n plus b is also in big O of n squared, right? Because in order to satisfy this inequality, in order to satisfy an plus b is less than or equal to c times n2, we just need to properly choose c and make a choice of n0. So it's just like the way we compute the bigger root for a quadratic function, so that for any n that is larger than this number, right, we can always have this inequality hold. Therefore, in this case, n squared is a loose upper bound for a times n plus b, right? Because n squared doesn't give a lower bound on this linear function. It's just a very loose upper bound. It makes sure that the linear function will never outgrow the quadratic function, but a quadratic form is never a lower bound for a linear function. So to restate what's said in the previous slides, when we say Fn equals big O of g of n, we are merely claiming that some constant multiplying g of n is an asymptotic upper bound for Fn, right? But we have no claim about how tight an upper bound it is. So, for example, in this comparison of function, a linear function n and a quadratic function n to the power 2, n squared, then n squared is of course a upper bound of n, but it is not tight. It can go very fast, but it's never a lower bound for n, and it's not very tight. Okay. So, but we notice that in some other textbook, the big O notation is confused with theta notation, or no theta notation is introduced. Just the big O notation is used to describe a tight bound. So that's not what we use in this course. So we have defined the tight bound using a theta notation, and big O is just a loose upper bound. So now finally, let's look at the big omega notation. So just as big O provides an upper bound for a function, big omega notation provides an asymptotic lower bound on a function. So formally given g of n function g of n and the big omega of g of n is a set of functions that satisfied there exist positive constant c and n0 such that Fn is greater than c times g of n for all n that are greater than n0. So in this intuitive plot, the big omega of g of n means that to the right of n0, Fn is always above c times g of n. Okay, so a tricky part for big O notation is that because it's a lower bound. Therefore, it means no matter what particular inputs of size n is chosen, the running time on that input is at least a constant times g of n. Therefore, we need to consider the best case of inputs because we want to find the lower bound. Therefore, we need to consider the best case. For example, in the insertion sorts, we know that the worst case is theta of g of n, theta of n squared. But for the best case of insertion sort, it runs in linear time, right? So now we have introduced all three asymptotic notations of functions, and there is a quite straightforward relationship between the three of them. So if you look at this theorem, so for any two functions, fn and g of n, we have fn equals theta of g of n if and only if fn equals big O of g of n and fn equals big omega over g of n. So that means if we want to show g of n is a tight bound for fn, then we want to satisfy that it is a upper bound for fn and also a lower bound for fn. Right? That's quite straightforward. And we usually use it to prove a tight bound from upper bound and lower bound using this relationship. So that's it for the part 1 of lecture 3. And I hope you liked this video, and I will see you in the classroom on Thursday for the part 2 of lecture 3. See you.